This is Lecture 6A for Calculus 2, the area between curves. Recall from Calculus 1 that the definite integral was often called the area beneath a curve. For example, if we integrate sine theta from 0 to pi, the answer is 2, and we say that is the area, and truly it is the area, between this red line, which is sine theta from 0 to pi, and the x-axis. Sometimes the answer from the value of the definite integral was negative. This is the case if we integrate sine theta from pi to 2 pi, and we get, as you see, minus 2. We tended in the past to maybe be a little wishy-washy about this and say, well, you know, the negative sign is there, and it really is the area between the curve and the positive x-axis. But now we have to be more precise. We have to really be able to evaluate that area as positive if it needs to be positive, and negative if the negative answer has certain meaning. For example, if you are working for, say, a construction company and you need to be able to pave some modern shaped parking lot that is bounded by a straight line and the sine of theta, you need to be able to calculate the square yardage of whatever it is you're going to pave that parking lot with, and you need that answer to be positive when you need it to be positive. Sometimes, though, this answer turns out to be negative, and that can have meaning when you're discussing, for example, the location of several particles or several moving objects, or when you're talking about the relationship between your cost and revenue functions in business. There are several cases to consider. We're going to start with the idea that we want this area to be positive, and we're going to begin with the easiest case. So now let's compute the area between the two curves. One is marked with red and one is marked in blue. So let's say that the red curve is the graph of some function f of x, and this curve down here, the straight line, is a graph of some function g of x. What we want is the area between these curves, right here between the red line and the blue line. This is a calculus problem. To do this, we take advantage of the linearity of the integral operator. Right. So let's recall what the linearity of the integral operator is. If I take the integral, say, of those two functions f and g, and I multiply f by some function alpha, or some number alpha, and I multiply g by a number beta, let's say dx, then this is equivalent to alpha times just the integral of f plus beta times the integral of g. Okay. How this applies to the area between the curves is that to get the area between the curves, first I calculate the area between f and the x-axis. So that this is the integral of f dx. That will give me the integral between the red line and the x-axis. Here we're going from 0 to 20. This is a definite integral, so we'll go ahead and put the limits on 0 to 20. Fine. Now I calculate the limit, or I'm sorry, the integral between g of x. This gives me all the area between the blue line and the x-axis. Then I subtract the two. By subtracting the two, I subtract off this area down here, and I'm left with what I wanted, which was the area between the curves. I'm going to erase some of the things on the screen now, and then I'll be able to write this expression as you see at the bottom of the page. So here's what we've got. We have that integral from 0 to 20 of f of x giving me the entire area beneath the red line. I'm subtracting off the area between the x-axis and the blue line, which is g of x, and the result is the area between the curves. Using that linearity property, I can write this as the integral from 0 to 20 of f minus g dx, and that's what's written down here, and that's the expression down here at the bottom of the page. So if you want the area between the red and the green curve between the function f and the function g, this is a definite integral. You take the integral from a to b, which is the interval of interest to you, subtracting f minus g, take that integral, and you will get the area between the two curves. Now the nice result we saw in the previous slide, where f was that red line and it was always greater than the blue line, which was g of x, and we wanted the integral, the area between those two curves. You only get that nice positive result when f is greater than g, okay, for all of x and ab, which is your interval of interest. The first few of the homework problems are exactly this type, so to get a little bit handle on how to do these kind of problems, I'm going to go look at the homework. Here is homework problem number 1 for homework 6A, and you're given two curves. F is e to the x and g is 3x. There's two parts to this problem. One is to graph the curves using a computer graphing routine, and we're going to graph them between x equal 2 and x equal 4. Then shade the area between the curves. You don't have to do that on the computer. You can do that by hand. And the next is to compute the area by evaluating this definite integral. So this is exactly the problem that I showed earlier in the on the slides for the lecture. So I'm going to go ahead and do most of this problem just to show you what I expect. The first thing is to graph the curves using a computer graphing routine. You can use any one you want. I'm going to demonstrate using dplot. If you want to use dplot, just let me know, and I'll let you have access to the license for the semester. Okay, so here is dplot. And what I have to do here, and it's similar in other routines, is first I have to tell it what curves to plot. So I go to Generate, and here I find y of x. Move this onto the screen so you can see it. All right, the first one was the exponent, e to the x, and that's exp to the x. You can get a list of functions to see how to put that into your routine. And then I want x to go from 2 to 4, give it so many points, and here we go, and it plots it automatically. Then I want to put the other curve on there, which was 3x, so that's 3 times x. Again, limits of 2 to 4. There we go. All right. Maybe that's hard to see, so I can go here and change the colors. Under colors, and I'll make one red and one blue. There we go. The red line is e to the x. The blue line is 3x. You can see that the red line is always greater than the blue line, so we have this easy case where we just have to evaluate the integral. And the area between the curves, actually in this case, I can fill it in. You don't have to do this on the computer though. I want between e to the x and 3x. I pick those two. Let's see. I'll use gray. You have all these options. Try to make it look a little bit professional when you get done. There we go. That's the area I want. That's the area between the curves. It will be positive. I'm going to take the integral of f minus g. Now we're back looking at the homework. The second part says compute the area between the curves by calculating the integral from 2 to 4. That's your definite integral of e to the x minus 3x, which is easy to do. The next homework problem looks a little more complicated. You have only one function, and that's 1 minus the cosine of x sine x, and you need to graph the curve between x equals 0 and x equal pi, then shade the area between the curve and the x-axis. That's the area to compute. Right now you don't know if this function is positive, negative, if it goes both positive and negative, so that's what graphing the curve will do for you. Then you calculate the area beneath the curve. And when you do that, I'll graph it in a minute, but if you want to calculate the area beneath the curve, then that is a definite integral. You're integrating, your limits of integration are 0 to pi, okay? And the function is 1 minus the cosine of x times sine x dx. You would generally do f minus g, okay? Let's talk about that in a minute. So if I want that integral, the area between the curves, I've got f minus g here, dx. So here's my f, but what is g? If you're talking about the x-axis, then that's the line. G of x would be 0, right? Because that would be the x-axis. You don't have to bother with that, so you just go integral of f of x dx from 0 to pi, and that will give you the area beneath the curve. This is a little practice using substitution. Obviously, what you're going to substitute is that let u be 1 minus cosine x, and then you can work out the rest of the problem from there. Let's go back to dplot and graph this function. just so you can see dplot one more time. Okay, so here's dplot again. I'm going to generate a function, and it's y equals 1 minus cosine of x, in parentheses, times the sine of x. And I want to go from 0 to pi. Most of these graphing routines know pi as pi. And here we go. All right, here's the x-axis. I can make that a little more clear for you. Axes only. And let's cross. Here we go. All right, here's your curve. 1 minus the cosine x sine x. You can see that it is always positive. By computing this integral, we're going to get the area beneath this curve. Now we're going to look at a little more complicated situation, and that's when the functions, so to speak, change places or trade places. Before, we always had the f function greater than the g function. If we use our same color scheme as before, the red function is f of x, so here's your f, and here's your g, is this blue line. Well, in this region, f is greater than g. Okay, so you have some negative excursions here you might have to wonder about, but f is greater than g. Okay, over in this region, f is less than g, and in this region as well, f is less than g. Right. If you take the integral as before, which was just the integral of f minus g dx, then the answer here has a chance to be positive. This will be positive here, but this integral will become negative, and this will become negative. Okay, because you're subtracting f minus g, and that will be the result. So if you really, however, want this area, you want the area in here, and the area here, and the area here. Think again that you're paving a parking lot, and you really need to know these areas. You don't need something turning out to be negative and subtracting off your total. So you want these. Okay, the solution is to take the absolute value of f minus g. And that's shown right here. Okay, so the area, this is the expression for the area between the curves. A equals the integral from a to b, which is your region of interest, and the integrand is the absolute value of f minus g dx. At this point, we have to digress, because taking the absolute value of a function is not straightforward. Or rather, it's straightforward once you know how to do it. So in this slide, we're just going to consider the integral of an absolute value. If we start with a very easy function, let f be the absolute value of x, or just say we're taking the integral of the absolute value of x, this answer is a modification of the power rule. Remember that if you had the power rule and you integrated x dx, you would get x squared over 2 plus c. Oh, this should have a c on the end of it, shouldn't it? Okay. You would have x squared over 2 plus c. Well, when I look up at this answer, I see the 2 here, and I see 2 x's, but one of them is in the absolute value sign, and one of them is out. This is the answer for the absolute value of x. Okay. You can extend this easily to the definite integral. Now, if you have a more complicated function, like a sine wave, cosine wave, or as in our examples before, you might have the absolute value of e to the x minus 3x, the answer is not given in a closed form solution such as this. What you have to do is look at the functions. Look at f minus g, and you take that integral and you break it up. Let me get my highlighter here. You break it up into several integrals based on regions where the function, or the difference of the function, is positive and where it's negative. Okay, so that will give you, that's how you take the absolute value of a complicated function. Let me write that out for a second. Okay, so I'm integrating some function. Let's just do the absolute value of f just to be demonstrated, and we're going to take it from, say, a to b. Okay, let's say that f is greater than 0 from a to c, and that f is less than 0, square bracket, c to b. Okay. So I break this up into two integrals. One, I'm going to go from A to C. F is positive there, so that's fine. Now, between C and B, F is negative. I use that result, and I subtract off this area. And that will give me the integral of the absolute value of f of x. So again, I have to look graphically, algebraically, I've got to look at it and find out the region, the intervals, subintervals, where f is positive, and the intervals where f is negative. And then I break this into two integrals. You know, at this point, I've dropped the absolute value signs. So here's an example. Say I want to integrate from 0 to 2 pi of the absolute value of the sine of x. Okay. So I would have to recall that sine is going to be positive from 0 to pi. Then it's going to go negative from pi to 2 pi. So it's positive here. It's negative here. I'm talking just about the function itself. So I take this integral from 0 to 2 pi and I break it up into two subintegrals. One's going from 0 to pi, where the sine of x is positive. Okay, and here I'm going to go from pi to 2 pi, where sine of x is negative. Of course, now I take the absolute value, which means I'd have to multiply by a minus 1 in this region. So those are my two integrals. When I evaluate them, I do get the area beneath the curve. But if you graph it, this is for 0 to pi. This is a region from pi to 2 pi, but because I've taken that absolute value, this is also positive. If I looked up here, I would get the sum of the area here and the sum of the area here, and that would be and have a positive answer. Otherwise, of course, I would have 0. Now for this particular lecture, of course, we're looking at the area between the curves f and g. So let's extend the result we just talked about. Now we have the area from a to b of the absolute value of f minus g dx. This will give us a positive value for that area. To evaluate the integral, we divide this integral from a to b into other integrals based on regions where f is greater than g and regions where f is less than g. So here's an example where we want to find the area between the curves cosine x and sine x. Here's cosine. In this case, it's in blue. Sine x is in g. So I want the positive area. I want the sum of the areas here, in here, and here. To do that, I take the integral from a to b. In this case, it's going to be from 0 to 2 pi. You can see the 0 here and the 2 pi here. And then I subtract the two functions. It's cosine x minus sine x, but I have to take the absolute value. To evaluate this integral, I look at the functions f and g, or f minus g, and I find regions where f is greater than g, in which case that absolute value will be positive. And that is right here for between 0 and pi over 4. And over here, between 5 pi over 4 and 0, again, f is greater than g. In between here, it's less than g. F is less than g. So those are the two, or the three integrals I divide this into. One is going to go from 0 to pi over 4. Then from pi over 4 to 5 pi over 4, then from 5 pi over 4 to 2 pi. Okay, so here's the problem worked out. I broke it up into the first integral is going to go from 0 to pi over 4. In this situation, cosine x minus sine x is positive, so this is the absolute value of cosine x minus sine x between 0 and pi over 4. Then I'm going to go from pi over 4 to 5 pi over 4. Taking the absolute value of here would be multiplying this by a negative sign. Here's that negative sign which I put out in front. Okay, and I take that integral again from pi over 4 to 2 pi. The function f minus g, cosine x minus sine x, is again positive, and so that gives me my third integral. And here's the result. So it's, as you would expect, we've got this area in here, and the result from this is going to be positive. Because of how we've done the integration, this is going to be positive as well, and this is going to be positive as well. So if we're back to our canonical problem of paving a parking lot, and the parking lot happened to look like this, well, we'd end up being able to compute how much asphalt we need. Actually, we're going to have a bit of a problem here because this is going to be 0 because of the negative excursions. Looking at the homework again, this is homework 6A, problem number 5. We have the same problem that was demonstrated in the lecture with a difference in sign here. In this case, though, the function f of x is going to be the sine of x. G is going to be minus the cosine of x, and you need to graph it between 0 and 2 pi. So the first part is to graph it, find the regions where f is greater than g, find regions where f is less than g. That is how you break up the integral, which is given down here for computing the area between the curves. So I'll show you dplot one more time just to get you used to it. Okay, here's dplot again, the one I use, general, and I'm going to generate the curve. The first one was the y equals the sine of x, so I put sine parentheses x in parentheses. I want to go from 0 to 2 pi, so I can go 2 times pi. That will give me my limits, and there's the curve. Now if I want to plot the other one, I plot another curve, minus cosine of x, so minus cosine prin x prin, again 0 to 2 pi, and I get this curve. I want to make them a little bit clearer, so I'll go to colors and edit the colors, put the second one blue. This will be my, okay, so the red line is my function f, the blue line is the function g. The red line is sine of x, the g line is minus the cosine of x. And I'm going to find regions where f is greater than g and regions where f is less than g. It's a little easier if I change the number format to look at pi's, and I can do it right off the graph, or you could have done this analytically too. Okay, so if we look at the curve, we can see that from 0 to 3 pi over 4, f is greater than g. All right. From 3 pi over 4 to 7 pi over 4, f, the red curve, is less than g, and then we go from 7 pi over 4 to 2 pi, f is greater than g again. And those were the regions you were looking for. So you translate the result back to the homework. So this integral here would be 0 to 2 pi, of the absolute value sine x minus a negative, so it's going to be plus cosine x, absolute value dx. Because you're taking the absolute value, you have to break it up into those integrals. 3 pi over 4. In this region, sine x plus cosine x was positive. Okay, so that just becomes sine of x plus a cosine x dx. Then the next went from 0 to, I'm sorry, it's 7 pi over 4. This was 3 pi over 4. And then you have the same. I'm just going to write f minus g to save some room. But in this case, I will take the absolute value. That will mean multiplying by a negative sign, so it becomes negative. And then the next is 7 pi over 4, going all the way to 2 pi. In this case, there's no change in sign. And you substitute f minus g, of course, is sine of x plus the cosine of x. I'll show you these results graphically. We want the area between the curves from 0 to 5. Well, 5 is out here. I'll just put a box for it. And if we look graphically, and then you can verify this algebraically, from 0 to 3, this region right in here, x squared is less than 3x. Okay. From 3 to 5, x squared is greater than 3x. This tells us how to break up the integral from 0 to 5. So we break it up into one integral going from 0 to 3, then we break it up into another integral going from 3 to 5. And taking the absolute value in the region 0 to 3 means multiplying x squared minus 3x by a negative sign. Here's the negative sign right here. Okay, then we go from 3 to 5, x squared minus 3x is positive, so there's no change in sign. You've probably seen enough examples of how to evaluate the absolute value of a function. So now we'll look at a related case in which the area between the curves can be both positive and the negative can have meaning. In this case, we do not take the absolute value. We simply integrate the difference between the two functions. There are two applications, two important applications for this. One is the distance between two vehicles. If we take the integral between of f minus g, where f is the velocity of one vehicle and g is the velocity of another, when this integral is positive, it means that the f vehicle is in the lead. When it's negative, it means the vehicle whose velocity is given by g of t is in the lead. Another application is looking at the profit when you're given the marginal revenue and the marginal cost. That's one of the homework problems. Okay, here's an example of a race, hypothetical race between a car and a plane. Let's say the car's velocity is given by this expression. Here's the velocity for the plane. Now I want the distance between the car and the plane. I will take the definite integral from 0 to t, t being any time, of the difference of the velocities. Okay, note here, which you probably remember from Calculus 1, that if I'm integrating from 0 to t, so if t is one of my limits of integration, it cannot also be the dummy variable under the integral sign, so I've used tau. Okay, and integrate with respect to d tau. Of course, what's the interval? The variable here is really a dummy variable. It goes away with evaluation, but you cannot have the dummy variable of, I'm saying this again, the dummy variable under the integral sign the same as one of the limits of integration. So when I carry out this integration, I might get results are positive or negative. If the result is positive, that means the car is in the lead. If the result is negative, then the plane is in the lead. Here's a graph of the two velocities. Let me get the pen out here because it looks like I need to trace those curves over. Okay, here is the velocity of the car. Okay, starts out faster than the plane catches up, and the car stops. Here's the velocity of the plane. It starts off at 0, and it increases. Okay, so what we're going to do is calculate the area between these curves. In this region, because I'm going to take the integral of the car, velocity of the car, minus the velocity of the plane. This is d tau. Okay, here the velocity of the car is greater than the velocity of the plane. When I evaluate this integral, this result is going to be positive. The reason for that is that the car is in the lead. Right. If I integrate all the way out to here, there was this positive area was part of the problem. Over here, I'm going to get, I'll put it in red, sort of a negative area. When these two areas balance out, then the plane and the car are at exactly the same place in space. After that, the plane will be in the lead. But I have to integrate all the way from here to here. At this point, like I say, when those two areas balance each other out, then it's going to be 0. After that, the result of the integral from here, shall we say way over to here, is now positive because these two regions have canceled each other out, and now you're just left with a positive result over here. Okay, and here's the result of that integral. So again, I integrated the velocity of the car minus the velocity of the plane no absolute value sign. At first, when I got out to say 10, so if the upper limit was say 0 to 10, then the result was positive. Okay, this is a result of the integration. The car is in the lead. When I got out to about 17, so that would have been 0 to 17, okay, then it was 0. The reason it's 0 is the plane is now caught up with the car. After that, the result is negative because the way I've set the problem up, the car is now lagging behind the plane. There's a very similar one to this involving two cars, one with a running start, in the homework. It's exactly the same idea. Set up the problem, integrate with two cars, so car number 1 minus car number 2, 0 to t. Okay, you're going to do deta. Once you evaluate this integral, you look at different values of t. If the value of this definite integral is positive for some value of t, that means car number 1 is in the lead. If it's 0, it means car number 1 and car number 2 are tied. They're at the same point. And if the result is negative, then car 2 is in the lead. Here's a related homework problem. Again, homework 6A, and this is problem number 6. In this case, we have the marginal revenue, which is really the derivative of the revenue function, which we're going to say is x squared over 6. Then we have the marginal cost, which is 4x. I'm going to graph these functions from 0 to 30 and notice the results there. You can figure that out. But to calculate the profit, I integrate, I'm going to say from 0 to some value a. Remember, x is the number of units sold. So I'm integrating from 0 to a of r prime minus c prime dx. When I evaluate that, I look for the point where the value of this integral is 0. Let me get the pin here. So I'm looking for p equals 0. I want the result. I want to find a such that this integral from 0 to a of r prime minus c prime dx equals 0. At that point, the profit is 0, means that the revenue and the cost, this is a prime here, the revenue and the cost will be equal. That's your break-even point. So again, I'm taking the area between these curves. In this case, I'm looking at r prime minus c prime. I'm integrating in general up to some point a. I want to find the value of a such that p is 0. That is the break-even point. So you can see this is very similar to the two racing cars or the car racing against the plane. Now, to finish the chapter, we have two more technicalities, so to speak. Sometimes you have the curves f and g, and you want the area enclosed by the curve. Up to this point, I've specified a and b. They were part of the problem. When they're not part of the problem, you are looking for the points, the values a and b, that's the two values of your independent variable, where f and g intersect. This is usually done algebraically. Just set f equal to g, and you will find those two values. Those become your limits of integration. Here's an example. Let's say f of x is going to be just 12, horizontal line. G of x is x squared. I want to find the points where these curves intersect because I want the region between them. Let me draw that a little bit for you. So what I have here is I have this is x squared, so to speak. Here's my y, here's my x-axis. Okay, then I have, that's the g of x. Here's the f of x. If this is 12. Okay, so this is f is equal to 12. Oh, I ran out of space there. Okay, so I want the region in between here. Okay, to do that, I have to find these points. To find where they intersect, you set f equal to g, you solve that algebraically, and you find it is plus or minus 2 at 3. So this point is negative 2 square root of 3. The point out here is 2 square root of 3, and those become the limits of integration. Right. You notice from here that 12 is always greater than x squared in this case, so we don't need absolute value signs, but you could put those on as well. Sometimes the way the curves are set up, or sometimes the way the functions are set up, it's easier to integrate with respect to y instead of x. That is no problem. I'll do an example here, and there's one in the homework problem as well. Find the area between, in this case, sideways parabolas. F of x equals f of y equals y squared minus 3. Ooh, that should be g of y. That's a y in there. Let me get the pin. This is a y. G of y equals minus y squared plus 3. These are just two parabolas that kind of aim at each other, one going in this direction and one going in this direction, and you want the area in here. To do that, again, the A and B are not specified by the problems, but you have to find these 2 points. You do that by setting f equal to g and solving. You find that it is plus or minus the square root of 3. That becomes your limits of integration. So you're going to go from negative root 3 to positive square root of 3, f minus g. But now you're integrating with respect to y, and that is not an issue. So here's your integral. Again, going from minus square root of 3 to plus square root of 3, the 2 numbers you found by setting f equal to g. Simplify the integrand and carry out the integration, and the following slide we can see the result. So here are the 2 sideways parabolas. By setting f equal to g, these 2 parts were found, these 2 points were found, as plus or minus the square root of 3. Carrying out the integration gives the area between the 2 curves right here. There's some homework problems where you're integrating with respect to y. If there are any problems with that, ask me questions about that in the recitation sections, or you can send me an email concerning that. These lectures are a little longer than they were for Calculus 1, but that's because I'm sort of embedding homework in them, homework help in them, which I think might be beneficial.